The kinetic molecular theory. So gases have a volume, or the volume of an individual particle is roughly 0, and that's just saying that the space that the molecule is actually taking up is nothing compared to the distance between molecules. The collision of particles with the container walls causes pressure exerted by the gas. Remember, pressure is force per area, so when it collides with the container wall, it exerts a force over a certain area. Particles exert no forces on each other, so gas molecules are not attracted or repelled by each other. Now that is also called an elastic collision, when you don't have a loss of net energy, or energy overall. The average kinetic energy is directly related to the temperature of a gas. So if you increase the temperature, the kinetic energy of a gas is going to increase. If you decrease the temperature, the molecules are moving slower, so kinetic energy also decreases. Real gases, however, actually have volume, and they do exert forces on each other because they have intermolecular forces. Real gases, then, don't conform to the kinetic molecular theory assumptions. How fast the gases are moving depends on temperature. We already said that it was directly related to kinetic energy. The higher the temperature, the greater the velocity. At the same temperature, the average velocity of a molecule depends on the molecular weight. A heavy molecule will be slower, and a lighter molecule will move faster. At the same temperature, though, they have the same kinetic energy. So we can relate kinetic energy and velocity by using the root mean square velocity. So you have the root mean square, and that's equal to the square root of 3 times r times t divided by m, where m is your molar mass. But notice that it has to be in kilograms. We don't normally use molar mass in kilograms, but for this particular formula, you do need to use it. The other change that we have is in the r. Because we're talking about energy, we have to use a different r value. So r equals 8.3145 joules per mole Kelvin. We can also calculate the kinetic energy by using kinetic energy is equal to 3/2 RT. Notice that the kinetic energy does not depend on the molar mass. So if you're at the same temperature, no matter what gas you are, you're going to go at the same, or you're going to have the same kinetic energy. Again, we have to use this different R value because we're talking about energy. So, for example, calculate the average kinetic energy of methane molecules in a sample of methane gas at 273 Kelvin and at 546 Kelvin. So at our first one, kinetic energy would equal 3/2, and then we want to use that new R value, 8.3145 joules per mole Kelvin times 273 Kelvin. Don't forget, I want to see that you cancel out your units. Here we're left with joules per mole, so kinetic energy, how fast they're moving per mole. And we would have 3.48 times 10 to the third joules per mole. So each mole of my gas would have this amount of energy. Now at the different temperature, kinetic energy would equal 3/2 using the R value for energy, and that is given to you in your reference table, times our new temperature. Again, our Kelvin would cancel, leaving us with joules per mole, and we would have an answer of 6.81 times 10 to the third joules per mole. Alright, calculate the root mean square velocity. So the root mean square is equal to the square root 3 times R, and we're using the R value that has for energy, times the temperature, 273 Kelvin, divided by 0.016 kilograms per mole. Remember, you have to be in kilograms. If we look at the units, if we look at the units, a joule is equal to a kilogram meter squared per second squared. So really we can go in there and we can change joules to kilograms meter squared over mole Kelvin second squared. And then if we look at our unit cancellation, kilograms will cancel. That's why the molar mass has to be in kilograms. Moles cancel and Kelvin cancels. Since we're taking a square root, our answer is just going to be meters per second. So when we calculate this, and please make sure you do all of the math before you take the square root, you should get 652 meters per second. If you think about it, that's really fast, and it should be because gases move very quickly. Alright, we can do the same thing at a temperature of 546. So the root mean square is equal to the square root of 3 times our R constant for energy, kilograms meter squared, over mole Kelvin second square, times our new temperature, 546 Kelvin, divided by our molar mass in kilograms, our units, kilograms would cancel, mole would cancel, Kelvin would cancel, and our square root on the meters in second would go away because we're taking the square root. So plug all that into your calculator and you should have 921 meters per second. Effusion and diffusion. Diffusion describes the mixing of gases. It's the rate of diffusion is the rate of gases mixing. Effusion describes the passage of a gas into an evacuated chamber or passing through a small opening. So this picture down here shows the effusion of a gas. To calculate the rate of effusion or diffusion, we use Graham's law. Graham's law says that the rate of 1 divided by the rate of 2 is equal to the molar masses of the lighter particle divided by the molar mass of the heavier particle. We don't typically use rates, and I just noticed that that should be a 2 and a 1. We typically look at it simply as one value, not as a fraction. Alright, so one way of separating oxygen isotopes is by gaseous diffusion of carbon monoxide. The gas diffusion process behaves like an effusion process. Calculate the relative rates of effusion of, and then it gives us 3 sets. So 3 sets of isotopes, we're going to calculate the rate of effusion 3 times. So if we look at our first set of isotopes, the lighter one, or if we figure out the molar masses, I'm sorry, I just confused myself on the problem. We're looking at the relative rates between these sets of isotopes. So if we look at carbon 12 and oxygen 16 compared to carbon 12 and oxygen 18, the heavier molar mass of oxygen 18 and carbon 30 would go on the top, grams per mole. And then the lighter molar mass, 12 and 16, 28, would go on the bottom. Divide it, take the square root, and it has 1.04 as the rate. What that means is carbon-12 and oxygen-16 are going to diffuse 1.04 times faster than carbon-12 and oxygen-18. Alright, so if we look at the mixture of carbon-12 and oxygen-17 to carbon-12 and oxygen-18, again, the heavier molar mass, 30, would go on top, divided by the lighter molar mass of 29. Divide, take the square root, and you get 1.02. So notice that the oxygen-17 and oxygen-18 combo is actually pretty darn close to each other. It just is going to effuse at a rate of 1.02 times as fast. So the only other comparison we have is between oxygen-16 and oxygen-17. Again, the heavier molar mass goes on top. Oh, I'm sorry, 8, yeah. So that would be 29 grams per mole. And then the lighter one, 28 grams per mole, would go on the bottom. So again, we get a rate of 1.02. An ideal gas versus a real gas. An ideal gas is hypothetical. No gas exactly follows the ideal gas law. Some may come very close, and the way they come very close is because they're at a low pressure and or a high temperature, usually a combination. So at low pressure, our gases are allowed to expand, increase the volume, so they are farther apart, they're not interacting as much, so their intermolecular forces become weaker. At high temperature, the gas is moving more, and so it will spread out some more, and again, our intermolecular forces won't come into question. So ideal gas behavior is thought of as the behavior approached by real gases under the certain conditions of low pressure and high temperature. Real gases, we must correct the ideal gas behavior when at high pressures, smaller volume, and low temperatures, because the attractive forces do become important. The van der Waals equation uses the constants A and B to account for the high temperature and the low pressure, and they depend on gases in question. Alright, and I realize this page number is wrong, so make sure that you fix this. The constants for A and B are found on page 212 of your textbook. So the A constant corrects for the pressure. The B constant corrects for the volume. So calculate the pressures exerted by 0.5 moles of nitrogen in a 1 liter container at 25 degrees Celsius. First, we're going to use the ideal gas law to solve for that. So the pressure would equal 0.5 moles times our R value. I'm going to use 0.0821 liter ATM divided by mole Kelvin times our temperature, 298 Kelvin, divided by our volume. For units, mole would cancel, liter would cancel, Kelvin would cancel, leaving me with ATM. So we would have an answer of 12.1 ATM. Now we're going to use the van der Waals equation to see how different it would be if we thought about it as a real gas. So I'm going to look on page 212 for my constants for nitrogen. And A is 1.39 times my moles divided by my liters. And we're going to square that times our B constant, 0.0391. Again, I've got those constants off of page 212. Alright, so if I multiply all this out, we'll look at the algebra individually here. We get 0.348 atm plus P and 0.9805 liters, and that equals 12.24 liter atm. So if we divide both sides by liters, our pressure, 12.24, divided by 0.9805, minus 0.348 atm, our pressure is 12.13 atm. So we're going to compare the results. In this case, the ideal gas law is very similar to our van der Waals equation. Why would that be similar? That's because we are at a low pressure and a high temperature.